the amount of change that we can push through the business really tallies with the amount of points we can gain. So we know that if we need to be, winning championships or winning races, we need to be able to push change through the business in order to be competitive and be at the sort of sharp end of the race results. And so having the openness of architecture and the ability to customize where we need to is really important, because as an F1 team, you can't go and buy F1 specific things off the shelf, so that they don't exist.
Welcome to Season 3 of the Next Generation Design Podcast. I'm your host, Jennifer Piper. Today, we're discussing the ins and outs of the design process at Oracle Red Bull Racing. In this episode, I welcome the head of CAD and PLM at Oracle Red Bull Racing. He tells me about the changes he's seen in their process over the last decade, the importance that software flexibility has in their success, and he's dispelling a prevalent myth about Formula One. Before we begin, let's meet today's guest, Dan Watkins. Dan, can you tell our listeners a little bit about yourself?
Hi, Jen. My name is Daniel Watkins. I am the head of CAD and PLM at Oracle Red Bull Racing. I've been working here for the last 10 years.
Thanks so much for joining us today, and welcome to the podcast. Can you tell our audience a little bit about the background of the Oracle Red Bull Racing team?
The Oracle Red Bull Racing team has been here for about 18 years, and we've been partners with Siemens for the entire time. In fact, we were partners with Siemens before we were Red Bull. So prior to being Oracle Red Bull Racing, we were Jaguar Racing, and before that Stewart Grand Prix, and Siemens were part of that journey too. And we're based at Milton Keynes in the UK, wholly based here with the exception of the fact that we have a wind tunnel about 30 miles away from this site here in a place called Bedford. The main campus here in Milton Keynes holds around sort of 800 staff that work to deliver our car to our two drivers. That's increasing now because we're deciding to get into the development of Formula One engines or power units. And so that number is going to increase over the next few years as we stand up a new business unit to support that activity.
As you said, you've been with the team for the last decade. How have you seen things change in that span of time for the team?
I've seen a fair amount of change in that time. The team has been winning, the team has been not winning. Throughout that time, we've been partnering with Siemens and using the technology that you guys provide to us to help us get onto the top step of the podium again, which is what we did last season.
That's wonderful to hear. Now, I'd like to jump right into the fun part of your job. What can you tell us about the design process? Where does it all start?
Our design process is effectively an iterative loop. We start with a concept, normally from an aerodynamic perspective. So if we take that's probably the most common sort of entry point. And we take that concept from a CAD perspective and we mock up multiple flavors or variations of that concept. And we do that digitally using the Siemens toolset. So NX is the CAD tool that we use.
And what comes next in the process? What are you looking for at this point in the design?
We take the concepts that we come up with from an aero perspective and we virtually validate those to see which ones will likely yield the best performance. And we use that in a CFD process, so computational fluid dynamics. So a validation of those design concepts. We've got a loop in that process that allows us to push 3D models from NX into our CFD process, and that runs on supercomputers. And then we analyze the output, and the best ideas based on the results that we get we then take forward to sort of the next stage in our process, which will either be a wind tunnel, where we start manufacturing parts at a scale. So we have a scale model of the car, so 60% scale model of the car that runs in the wind tunnel that I talked about earlier, that's over in Bedford. And there we analyse those results to see if they sort of correlate with what we find in CFD. And then once we've done that analysis and we've understand which one of those then are best in a physical environment, we would then scale those up to do like a full-size car design. And at this point, we're back into NX again, and we're looking at making the sort of aero concepts able to perform in a real world function, so i.e. when we hit the track. And that means that we're looking for not just aero performance, but also sort of durability. We're checking for fatigue, that the parts can last. And so here we get into another set of virtual validation tools using sort of FEA, so doing FE analysis to make sure that they're structurally capable. And again, we're using much of the Siemens tool set from a design simulation perspective to do that analysis.
What kind of physical testing is involved in the process?
Once we've done that from a full-size perspective, we then commit to manufacture parts for testing. So we have a research and development element to what we do as well. So we've got a lab where we take those parts that we manufacture, we put them into the lab and we test them to see whether the results that we get, again, with a physical part match what we got from a virtual validation in FE. And if we're happy, then we start manufacturing parts to go on the car. Because we're limited on testing, the only time we really get to test any of this is typically when we go racing, or at the beginning of the season when we have sort of two test periods before we start the season proper. But in season, that test is normally in the practice sessions before a race weekend. So the regulations of the sport dictate that you can't just make parts and then run them on a track.
So then what needs to happen to get the final design of the car over the finish line?
We take new ideas and new concepts. Once we've manufactured them, we take them to the track. And the first time we ever see them perform is on a practice session, say on a Friday of a race weekend. And that's where we then really understand whether the virtual validation that we have in CFD and FEA then come true in reality when we race it around a track. If the results that we see on track are good, so the parts are better, then those parts get to go racing. So they'll go racing that weekend. But if they don't correlate and they don't give us the performance we expect, then they don't go racing. But yeah, whatever we learn from that, whatever learnings we get, we feed that back into our design loop and we do it again. So we come back after we've been racing, we come back the following week, and then we feed that back into that design loop where we go again. So we then look to improve the parts and we go round that iterative loop from concept design to virtual validation, manufacture, and parts go to the race.
Wow, so it really is quite the rigorous process. You talked a little bit about some of the products that you use in the suite of Siemens tools. Can you tell us some of the specifics there?
One of our key strengths, or an area that we think we're really quite good at, is the design and manufacture of composite parts. So a hugely important aspect of any Formula One car, and an area of the car that you can often gain most performance on track through bringing better updates to the car from an aero perspective that are typically composite in nature. So over the last, I'd say, 2 years, we've pushed the digital side of that composite design element by using FiberSim. So FiberSim is a Siemens product that's part of the NX toolset, and we really use that to drive the composite manufacture process. So we generate the ply layout and layups in FiberSim, and we output that information to help us develop our ply books. These dictate how we manufacture the parts, and we also use that information to drive our laser ply projection machines that allow us to project a laser onto a mold and then more accurately lay up the plies on that mold.
How has the introduction of these machines changed that process?
We used to do this manually. So we used to have very skilled guys and girls in composite manufacturing that would manually use sort of drawings and templates to do that. And the introduction of laser ply projection has really, really improved the sort of variability that we would see when you left it to individuals. However skilled, you would get variation. Now it's super accurate. So we get a very repeatable process. We get very little variation from person to person. And we've also reduced quite dramatically the amount of waste. The waste carbon fiber that we get as you lay the plies in. Typically, if you're doing it manually without the help of a laser ply projection machine, then you would overestimate how much carbon fiber you needed. And so therefore the waste material that you would trim off would be much more than we see now.
And I assume it must speed up the process as well.
One of the biggest benefits, aside from all those other things, are the speed at which we can do this. So we've sort of conservatively estimated that we get about a 30% improvement on some of our key parts in the manufacturing process. That really allows us then to sort of hand that time back to design to design better parts. So if we can save 30% in our manufacturing process and our manufacturing time, then what that allows us to do is give the engineers that are designing those parts more space, more time to design better parts. So better quality, more robust, and maybe faster, or hopefully faster.
I'd like to talk a little bit more about the software you're utilizing in your process. It sounds like you must rely on the digital twin as part of your design. Can you talk a bit about how that plays into everything?
We absolutely rely on having a digital twin of the physical car that we see on the track, and it's pervasive throughout the business. So we have a digital process that runs from sort of concept to track, and that process relies on that digital twin of the car. So we 100% model and design everything in CAD. We have a set of virtual validation tools from CFD to FE, also within the manufacturing space as well, where we virtually validate all of our manufacturing toolpaths so that we can have confidence that when we put parts on a physical machine to make, that we're not going to have any issues on the machine itself. We virtually mock up the assembly of the car, so that's available to the guys at the track.
I imagine that mock-up must be key when a brand new car is on the track for the very first time.
Particularly important at the beginning of the season when it's the first time the mechanics are going to have seen this new car. So we try and provide them a rich set of digital tools where they can see what this needs to look like and how this goes together as they're seeing these physical parts coming through for the first time. And then obviously we capture lots of data coming back off the car. So the car is a big instrumented device that then feeds us back information about how it's running throughout the race, and then enables us to act on that information and change what we need to do as we're going around a track. And then this is all fed back into our sort of key systems, Teamcenter being our PLM system, the core of our sort of design of our car, and that then stores the information that we need in order to design the car, and then helps us feed back into that and then electronically push data around to all of the various people that need it to enable us to make sort of better informed decisions and act quickly. So it gives people the ability to act quickly based on the right information being available at the right time.
So that flexibility is a chief factor in your success. How important is the openness of architecture and flexibility of software tools in your process?
I would say that they're really key to driving the speed at which we're able to push change through our business. And what we know through being here for 18 years, is that the amount of change that we can push through the business really tallies with the amount of points we can gain. So we know that if we need to be, winning championships or winning races, we need to be able to push change through the business in order to be competitive and be at the sort of sharp end of the race results. And so having that, the openness of architecture and the ability to customize where we need to is really important, because as an F1 team, you can't go and buy F1 specific things off the shelf, so that they don't exist. So because we've got some niche applications and some niche use cases, and so being able to extend the tools that we have in a controlled way really allow us to push the productivity of our engineers to another level.
Can you talk a bit about where FiberSim plays into all of this?
FiberSim is a really good example. So we touched on composite manufacture and composite design, and the fact that we're using FiberSim as one of our core tools now. Here we've used the sort of NX Open toolset to automate some of the key steps that we go through to get to the point where we can provide manufacturing with the information they need to feed their laser applied projectors, to the point that what we're seeing is that a process that would take probably 4 days to go through manually to get to that point, we've automated that down to probably 10 minutes with then double checking the work. And that's down to the openness of the tool set that we use and the ability to programmatically take away the tasks that would usually cause engineers to spend more time than we would like on the tools. But what it does do, it gives them the ability to then focus again on that quality of what they're doing, focus on being engineers or imagineering new concepts rather than having to work within the tools. And NX and Teamcenter are great for providing that architecture for us to be able to do that.
That's incredible. 4 days down to 10 minutes. That must make a huge difference in the process.
It makes a massive difference. We see the same in the design tools, where we can use sort of NX automation and a robust parametric modeling approach to really drive the number of iterations of an assembly. So take a front wing assembly, which is probably the most influential part of the aerodynamics on a car. We can really push the design and development of that through robust parametric modeling within the CAD tools, but also then with automation of that robust model, so that we can really churn through designs that we can then send to CFD, that we can then validate virtually and then move forward with. So it makes a huge difference, probably 5 or 6 times faster using the NX Open tools than we would be able to do if you were to manually do it. So it's significant.
I'd like to move on to the practical aspects of Formula One design. What would you say are your biggest challenges when it comes to designing a car? Are there any constants you tend to run into?
I'd say it's variable. So there are some constants. The constants being rule changes. So, I say constants being rule changes. We invariably get rule changes from season to season. So we almost bank on that being a thing that happens. And dealing with those rule changes can be a challenge. So understanding what the regulatory body of the sport, the FIA, are saying that we need to adhere to, and then correlating that to a set of rules that we then deliver to our engineers that they can then work within. And we often take those rules that are just documents of text and we convert them into geometry wherever we can. So what that allows us to do is bring that textual information into a 3D digital world to give space envelopes or volumes or car mock-ups that then our engineers can use to help them drive or be mindful of their designs when they're coming up with new concepts to make a fast car. that really makes a big difference.
Have you ever run into any issues with factors like cost?
So the FIA, again, our regulatory body, has enforced cost caps on the sports for all teams. And so we now have to be more mindful about where we focus our development. So then we have to have more confidence in what we take from a concept to a physical part, which means that there's a much bigger reliance on our digital tool set, so that we can, if we can digitally mock up more concepts, and we can do that faster, and then we can validate those concepts virtually using those same tools, then that means we can have more confidence in the parts that we take forward to manufacture, which is often where we incur the biggest cost before we do that. And so NX and the integrated tool sets within that, the NX portfolio, so from design to composite design and manufacture to the CAM tool, so we use NX CAM here to program all the parts. Having these things joined up and linked together really help us push that, so that we've got a high level of confidence in the parts that come out physically, such that we're not making things that don't work, because in an era of cost caps, that really hurts.
So how far ahead of the design process do you, as the team, get notified of the FIA's new rules for the season?
Ideally, we'd always like longer, but it's always tricky because new rules and regulations have to be agreed across all the teams also. So it's normally months, sometimes less than that, but usually but anywhere between a month and 6 months that you'll get notification. But that's a lot of work to do still to change what we do. And maybe if we look at the regulations for this season, was a new car, completely ground up, new design, completely different from the last car. The things that are the same are the fact that we've got 4 wheels, an engine, and then a driver in it, and then everything else around that is pretty different. But even the wheels are different this year. So we've got larger wheels, less tyre now, the tyre's thinner. That brings its own challenges in. And so we probably got a little bit more advance notice, but the rules weren't firmed up till probably late last year, Q3 or Q4, but you take a view on these rules, so you'll get some time to digest them, and then we're working on what we know, and then iterating on that as the rules become hardened.
It sounds like your keys to solving those challenges really lie in the tools that you're using to design and manufacture the car.
The digitalization of our workflows and processes and the tools that we use are really what we need to fall back on now, because we're limited on it everywhere else. So we're limited on resource, we're limited on cost, we're limited on time. So we haven't got more hours in the day or days in the week. We can't throw people at the problem now. So we have to look at the digital tools and the processes that surround those to help us drive us forward to still be competitive. And if we can put the same effort into that as we do for the car, then for designing and developing that, we do the same with our tools that we use to support our engineers, then that really is a key area for us to help us move more quickly. And working really closely with Siemens, so Siemens being our sort of longest standing technical partner, we're constantly working with you guys to help us look at the art of the possible. So what's next? What can we use now from this rich set of digital tools that you have that can then allow us to be better tomorrow than we are today? And that's really, really what we're looking to do, every day. And we rely heavily on the Siemens tools to do that.
Switching gears a little, are there any common myths you hear about the Formula One racing industry that you'd like to dispel?
We often get that we have a favourite driver, and the favourite driver gets a different car. So I can't remember or count the number of times somebody has said that. So you have a favourite driver and he gets a different car to the other driver and it's faster. And typically that's absolutely not true. And mainly because what most people miss is that Formula One has two championships. We have a Drivers' Championship and we have a Constructors' Championship. Whilst we're trying to win both, the one that impacts everybody here at the factory in Milton Keynes and at Bedford is the Constructors' Championship. That's the team one. That's the one we're all pushing to win. But everybody outside of the Formula One team, whichever team you're in, everybody looks at the Drivers' Championship as the one. But we're really focused on the team one. So it's the team one that we want to win. And that means that you need to get two cars round, two cars to the finish. You need to have two cars that score as many points as you can to try and win that constructors title. So we really don't favour one driver over another.
Is there ever a time when there would be two different cars racing for your team?
The only exception is if we've got a new exciting development and we haven't had time to make two lots and two lots of parts, just because some of the timescales are crazy here. So, we could have we've got weeks or days between races, and so trying to get parts designed and manufactured in that time scale are challenging. So sometimes you'll see that where we haven't had time to manufacture two sets, but typically the cars are identical. The difference being some drivers are bigger and smaller, so their seats are different and where the pedals are different. But yeah, generally it's the same car, two cars going around a track.
What role or influence do drivers have in the design of the car?
Well, obviously the drivers are sort of an integral part of the car. So it's all a connected system, the driver being in the loop. And he's or she, as the future may hold, will always feed back what they think about how the car is handling or driving. So they will feed back what they feel as they're driving that car. Then we will use that feedback to try and improve the car or change the car. So it's not typically a direct design, design this part in this way, but it's almost an indirect, well, we've put these new parts on the car and this is how it feels to drive. And so then we interpret that back and then that then influences maybe how we set the car up or how we then feed back to the engineers what we think about the design that we've just brought forwards.
You're allowing for that loop of feedback in order to make continuous improvements along the way.
That's correct. Whilst we've used our virtual simulation tools to figure out which parts we're going to go racing with, when we put them on the car and we see the results of that, the driver's feedback also forms part of that feedback loop. And within our sort of iterative loop is we have a virtual simulation, driver simulation. So we have effectively fancy PlayStations where the drivers can drive the setup of the car and drive the tracks, in that virtual simulator before we go to the track. So we scan all the tracks and then we drive the tracks in our simulator, and that forms part of that feedback loop too. So that's feeding into the process as well as the actual driver feedback when they get to race it for real.
So you have actual human feedback as well as that automated feedback. Now, how did the Oracle Red Bull Racing team manage through the pandemic? Were any of your processes interrupted, or were you still able to do your design work?
Like for most businesses and most organizations, it was a massive challenge. We've typically been a business that people come here to work, so they work on site. And, we put a lot of emphasis on a sort of internal collaboration, particularly in engineering. So we co-locate all of our engineers. We have a huge engineering office, and we've for years actively encouraged the face-to-face collaboration with people, because that's really the best form of communication. And if you can have those conversations directly with the person 2 bays down from you, then that really expedites how we're able to design and develop the car, and it makes a really big difference. even if we've got engineers in one building and engineers in another, the fact that you've got a gap between them prohibits that a little bit, even with all of the tools we have today.
That must have been a struggle then to continue to have that sort of collaboration.
So it was a challenge for us, but because we've over several years worked hard on the digitalization of our tools and processes, we were able to quickly spin up the infrastructure that allowed us to support remote working. So we had some before we started, but it's fair to say that the pandemic meant that we need to have an order of magnitude more. And so we were able to do that quickly. The digital tools that we had in place really supported that remote working process. And whilst it wasn't what we think is an ideal way, it really, really helped during that period, and still does today. We like to provide engineers some flexibility, and this allows us to do that. And the digital tools that we have sort of underpin the ability for us to do it. Having our processes electronic, so all of our sign-off processes are electronic, all of the delivery of information to the various users around the business is all electronic, and that then underpins our ability to be able to work remotely in a less disrupted way than some other businesses would have been able to do. In fact, we think it's probably a big reason why we were quite competitive last year and it led us to being able to win the championship with Max.
It sounds like you were really able to change and adapt successfully, even with that massive challenge. Congratulations on your success so far. We're definitely excited to see how it all turns out.
Yeah, fingers crossed. When November comes around, we're still at the top of both championships, because that's where we want to be this year.
We'll certainly be rooting for you, and thank you for sitting down with us. We've gotten some great insight into the design process at Oracle Red Bull Racing. Thanks so much again to Dan for joining us today. Thanks also to our listeners for tuning in to today's episode. Join us next time for more discussions about the latest in design, innovation, and software applications. I'm your host, Jennifer Piper, and this has been Next Generation Design.